Chapter 12, liquid, solids, and intermolecular forces. So we talked about gases back in Chapter 11, and now we're going to talk about the solids and the liquids. Let's talk about interactions between molecules. Have you ever thought about taste? And how does your body taste things? Where does that come from? Why do some things taste good and some things taste bad? What's exactly going on there? Yeah, there's taste buds on your tongue. It has something to do with that. It's actually a chemical interaction between the food and specialized cells on your tongue. There's receptors for different molecules that are in the food. And so most taste originates from interactions between molecules, the ones in your tongue and the ones in the food. You have these special receptors, and they only recognize certain kinds of molecules. That's why some areas of your tongue are better at tasting salty things and some better at tasting sweet, because they have more of that particular kind of receptor. This is the book's slides, and so they're talking about drinking coffee and how coffee tastes bitter. Yeah, I personally do not like coffee at all. But I understand that a lot of people do, and so I'm not going to hate on you if you like coffee. But there's molecules in the coffee that taste bitter, and when they interact with your taste receptors, then you get a sensation that your brain interprets, and different people interpret those sensations differently. But it comes down to intermolecular forces. And again, we use prefixes and suffixes a lot in chemistry, but in an attempt to be descriptive. Inter means between. So intermolecular, these are forces between molecules. These are not the forces within a particular molecule, but between two different molecules. And intermolecular forces are really, really important. They're essential for many physiological processes. How does that sugar molecule that we just talked about, how does that come in and fit into the active site on the enzyme? It has to do with the intermolecular forces. There are less specific intermolecular forces that exist between all molecules and atoms, and in fact, without them, we would have no solids or liquids. Everything would be in the gas state if we didn't have intermolecular forces. So they're pretty important. The physical state of a sample of matter, whether it's a liquid, a solid, or a gas, is going to depend on the relative strength of those intermolecular forces and the amount of thermal energy. So I think of the intermolecular forces as kind of like being Velcro, sort of a stick-togetherness. How sticky are the molecules to each other? Some of them are not very sticky at all, and some of them really want to stick together. Or I suppose you could think of balls covered in glue or something. Anyway, things that kind of stick together. So why isn't everything just stuck together? Well, there's also an opposing factor called thermal energy. And this has to do with the motion of atoms. All atoms are in constant random motion, and that random motion increases with temperature. So the molecules in the desk, they don't look like they're moving, do they? The desk is sitting there. I'm watching it, it's not moving. But the molecules in there are moving. They're just vibrating in place. You guys are right now in the solid state of students. I gave you that analogy earlier in the semester, solid, liquid, and gas state for students. You guys are solid right now because you're sitting in your desks. Are you moving? Not relative to each other, but you're moving. Some of you are taking notes, some of you are yawning or taking a drink or looking at the broken clock that's not going to help you know when this is going to be over. But you're there. You're breathing too. Breathing's good. So you're moving. Molecules and atoms are moving too, even in solid objects. And the amount of motion depends on the temperature. Temperature is a measure of the average kinetic energy of a substance. That's the energy of motion. And we sometimes use the term thermal energy as well. So when we increase the temperature of a substance, the particles move more. And if we get to a certain point, it will change how they interact. So if the intermolecular forces are strong relative to the amount of thermal energy, the sample is likely going to be a liquid or a solid. The particles are going to be held together. If the substance has a weak intermolecular force relative to thermal energy, they're more likely to be gases. Where with a gas like oxygen, the forces that want to hold the oxygen molecules together are very weak, and so it can't hold them together at room temperature and they fly off. I ran these together this morning in one video, so I'm going to do that again right now. So this is section 2. We talk about liquids and solids. And some of this is review, but reviewing is good. So gases that we talked a lot about recently are separated by large distances, and there's really no interaction between the particles. But in liquids and solids, the particles are close together. They're touchingly close, and so they are going to have interactions. The difference between the solids and liquids is the amount of freedom of movement. So in a solid, the particles are fixed relative to each other. You guys are sitting in the same arrangement that you were 5 minutes ago. And hopefully in 5 minutes you'll all still be here too. But in a liquid, like when we get up and move around the room, then people are in different positions relative to each other. You're moving around, and yet we're still all in the same confined space. So that's more like a liquid. Free to move around. In solids, they're fixed in positions, but they vibrate. Here's pictures. We see with the gas, there's a lot of space, and these guys are operating completely independently. They're not interacting with each other. In the liquid, the particles are much closer. And what's holding these together? Why are they not flying around the container like the gases do? It's the intermolecular forces. These are stickier, you might say. They're not actually sticky, but it makes more sense. So these have forces of attraction to each other that are stronger than these particles. And then the solid, the forces are even stronger, and they're holding them together so tightly that they're staying in this formation and they're not changing. And this accounts for some of the differences in the properties that we see for solids, liquids, and gases. Gases have low densities compared to liquids and solids. I'll go back and look at this picture and say, well, yeah, that's taking up a much larger volume than as a liquid or a solid. Density is mass divided by volume. Does the mass of something change when you melt it or freeze it? No. But the volume may change. When you turn it into a gas, the volume changes a lot. So gases have low densities. They have indefinite shape. They'll take on whatever shape the container is. They also take on the volume of the container, which is kind of weird. Because we usually can't see gases, and so we don't see them doing it. So we have very little personal experience with what gases do in terms of that. But they do have an indefinite volume. It's easy to change their volume. You can compress gases. And I think we are somewhat familiar with that. You can compress a gas into a smaller space. That's not true of liquids and solids. Gases are going to have weak intermolecular forces, and an example is carbon dioxide. Liquids have high densities compared to gases because they're so much closer together. There's not a whole bunch of empty space. They're going to also have indefinite shape. You pour water from one cup into a bowl and it changes shape. But they have definite volume. The volume doesn't change. They are not easily compressed. It's hard to compress a liquid, very, very hard. And that's the basis of hydraulic systems, is that you have a hydraulic fluid, you put pressure on it at one point, and the fluid will move and put pressure on something somewhere else. Awesome concept. They have moderate intermolecular forces. The forces are strong enough to hold them together, but not strong enough to lock them down into specific positions. And so they can move around. They're kind of sliding around each other. An example is liquid water. Solids also have high densities. Solids and liquids have densities that are roughly the same. But solids have definite shapes. When you think of ice cubes, Take an ice cube out of the tray and you put it in a bowl. Does it change its shape? Nope, it's still shaped like an ice cube until it melts, right? But then it's a liquid, so it's not a solid anymore. They have definite volume. Solids cannot be compressed. There are different kinds of solids. There's crystalline solids and amorphous solids. We talked about those. A crystalline solid is ordered. So you guys would be crystalline right now because you're sitting in rows. You know, if we got out a rug with circles on it and had you come up and sit on the floor like kindergartners, then you would be disordered, right? You would not probably sit down in neat rows on the carpet. So that would be, but you're still sitting and stationary relative to each other, so it's still a solid. Solids are going to have stronger intermolecular forces. The forces are so strong that they can't slide around next to each other anymore. They're locked into position. An example is sugar. And then there's pictures. This kind of goes overboard, but that's okay. So here we've got the particles of a liquid. They're very close together, but they're able to move around, take on the shape of the container. In ice, the crystals, the molecules form crystal shapes. They open up in this lattice pattern here, and they're stuck. And so that's why the solids retain their shapes.